Okay, so we're going to kind of split this in two, and Luke will take the second half. I'm Phil. I'm the PFA guy, if you've ever heard of the PFA model. You know, that was 11 years ago, so, you know, forgive me. So the nature of the task. A typical method we use in my lab is student stratification. I think student stratification works particularly good because you're typically having to set up a learning system and you're encountering new students, and you have to have a model for the new students. When you're trying to generalize to entire students, then it's like they're new students, and so that's kind of the procedure we've used. And this procedure, though, wouldn't transfer to the way the EdNet competition was set up, and we didn't really realize this immediately. And here in the EdNet, the test fold was splitting subjects. And so this causes a lot of difficulty, and this may be why Varun was showing us also fits that weren't on EdNet, is because you have to keep these huge tables of the prior data from the training set and then pass it over to the testing situation to be able to realize a model like this in the context that the competition was run in. And so we could create these huge tables, with 390 something thousand subjects, that if we're talking about a table of the skills for each subject, we're talking about massive tables. We did learn how to do sparse matrices. In theory, we might have been able to do this. We did have some success with some smaller tables with really fast lookups and so forth to try to keep track of the features from the training in the test. But it was a lot of work. So the tools we used, mostly this LKT package that we've written, and it's basically handles logistic regression models of almost any flavor, where you can specify, which column is your subject, which column is your KC, whether you want your subject to have an intercept, whether you want your subject to be fit with some sort of adaptive feature, whether you want your items to be fit with adaptive features, or you want your KCs to be fit with adaptive features. It's extremely flexible. And it was way too slow, though, when we started the competition, and that slowed us down, and it had to be basically rebuilt. And so we built it using liblinear, which is built on C++, I think, and so it's super fast. And data table in R, which is also very fast. Sparse matrices, which allowed us to be able to handle, like for instance, building the model matrix when you're talking about this many parameters, and you're trying to expand this matrix for your entire data set. It was quickly creating memory errors to create the model matrix to represent the one-hot encodings and so forth for some of these things, because there's like 1,300 content or 13,000 content IDs, as I recall, and so you need a parameter for each one, and so you need just to do that, you need a matrix that would be the length of the data 13,000 wide. So you can see how that caused a lot of data processing issues. And also, too, it kind of highlights that when you apply logistic regression in massive data sets, it's not so clear that the parameters are actually less. Also, dplyr, too. So too late, we realized that if we really wanted to do this the optimal way, we would need to create a strategy to model, to handle, to not do student stratification, basically, where we would create a model optimized for the test data fit rather than a model that fit entire student records. And so we developed a strategy to simulate the test set by kind of proposing that each student, started at a random time and distributed their data, so we could take out a section that would simulate the test set. And we knew we needed to then, compute our model in such a way that, we were using the features from the training for the window that we had taken out in order to compute the optimal model to fit the training. And so it became quite convoluted because of the data mechanics, actually. A lot of work with bookkeeping and not with building the models. So we did have a little bit of success in the competition. So we got to an AUC of about 0.74, 0.745 with two models that were relatively straightforward. Both of them used the content ID. So there's this table of one difficulty parameter for each item, basically, just like IRT. And one of them was, in fact, a one parameter IRT model where we had one parameter for each student, which we would infer from the test data. Luke helped me do that across the entire test set by splitting it into groups of about 20,000 students each and finding those parameters for each 20,000 students, and then compiling this table of the student parameters for all 390,000 students and for each content ID. So that's the second model here, which is IRT. The first model was more simple. The first model was just the content ID and a simple adaptive model of the student, which was essentially PFA, except without any KCs, with only one KC, where you just looked at the successes times a coefficient plus the failures times a coefficient. And so that was the adaptive model that would kind of home in on the student a bit. I think it was actually the log of those values, because usually taking the logarithms of the counts tends to work a little bit better in these situations. So that kind of confirms what Varun was showing with IRT in my mind. And also our offline results are suggesting that he's just about perfectly right on with the 0.77 as well. So we can develop various methods with the student stratification method, which I think is very similar to what he was using, and to trace the knowledge components. We were doing it where we were using the unique tag combinations, and there's about 1,300 different unique tag combinations, and we would treat each one of those as a KC. And that's one way to avoid splitting the data to have multiple predictions when there's multiple KCs for a particular event. We also tried using single tags. That's very difficult, like I was saying. There's some limited ways to do it, but basically they blew up memory too much for it to be very practical. And then also too, we've developed a method.
Phil,
Yeah.
just a simple clarification question. When we say unique tag combination, so that actually if there's lots of problems that are tagged with, say, Pythagorean theorem and equation solving, you made one tag called Pythagorean theorem equation solving?
So sometimes, KC 13 or tag 13 would appear with tag 14. And so we would treat the 13-14 pair as a KC. Now, if 13 appeared with 15, it would be a different KC. If 13 appeared alone, it would be still another KC. And so I think we got to 1,300 KCs with that method. And that was one method we tried, because it was even though it was really had a lot of parameters, it was still fairly easy to input into the LKT method and compute it pretty quickly. We also had a method where we were clustering the unique tag combinations, where we would have a method where we would calculate a matrix of their relationships according to the performance of each unique tag combination for each student, kind of a way of getting the relationships from the practice in kind of a raw format. And then we had this method where we would cluster that result to see which to assign clusters to each of the KC or to each of the unique tag combinations. And then we would be able to have essentially a new KC, which was the cluster of previous KCs. And so that could be done hierarchically in theory. I think with what we were already doing, we probably could have got to 0.77. In fact, we saw some that were 0.77. I'm not sure if they would have cross-validated at 0.77, but I think that eventually we would have cross-validated about 0.77. So again, I think it's suggesting what Varun was suggesting. And we were also looking at a lot of recency bias and also bias for early practice, which is essentially what windowing does. And so we have a mechanism like windowing. And, as I think maybe he was alluded to also, I think this is nice for one reason. It's not hard to interpret, right? Because everything is tied down to a unique tag combination or a tag or an item. And so you can really make a graph of the relationships and how things cluster together and what items are related, and how the content, how a designer of content then might use that information to put together units or something like that. Let's see. And that's Luke's turn now for the rest of it. Thanks.
Great. So should I share basically the same thing, or should I just tell you when to switch slides?
Oh, you're muted again. And
Sorry, I said you could just say next.
Okay, great. So yeah, I'm going to take a different kind of tact here to talk more about like what the function of these models is usually intended to be, which is to make predictions and help make pedagogical decisions for students. So we have a big focus here today on making models to as accurate as possible. But there's considerably less research generally on what to do with those predictions. So for example, like a decision rule. So if you've got 100 different items to practice, and some of them are well learned, some aren't, and you have a model that's making those predictions for you, the decision rule is just which item should be practiced next based on the information we have from this model. There have been some recommendations about, like, for example, practicing what's most difficult. So that'd be, the least learned item, which will provide large gains, right? But at what cost? Next slide. Great. So that black curve there is a hypothetical learning gain curve where there's some correctness probability on the x-axis. So that's the likelihood of them being correct according to your model, for example. And then on the y-axis is learning gains. And you can see there's less gains if it's very, very easy, and less gains if it's very, very challenging. And then somewhere in the middle, there's some kind of optimal point. But the important thing to note about this gain curve is that it's not taking into account the time costs. And so what I mean by time cost is when someone is successful on a trial, they answer the question correctly, they can be notably faster than if they were incorrect. Part of that can be because they don't need feedback all the time if they're correct. And if they fail, you presumably want to give them some feedback. And there's evidence that a successful attempt where you answer the question correctly can provide the same gains as when you're unsuccessful but are given feedback. And if you don't take into account this different time cost, you actually could be practicing according to like the wrong optimal point, right? So the learning per second will be different, even if the learning gains, when you irrespective of time cost, could be possibly 0.5 in this case. The learning per second shifts when you only have a 20% difference in time costs. So in this case, I'm using 20 seconds for a correct answer and 24 seconds for an incorrect answer, which I believe is actually pretty similar to what you'd find in the EdNet dataset. And so the point here is more to think about what we're doing with the models as maybe an even harder challenge than making models that are quite accurate. Because I think just to put it another way, what are the practical consequences of having a model with 0.8 AUC versus 0.78, and versus having a good versus bad decision rule? I'd argue that having a mediocre model with a good decision rule that's optimal is better than having the most accurate learner model, but no plan with what to do with the predictions. Do next slide. So yeah, just to sum up, pedagogical decision rules are a very important consideration and maybe deserve their own challenge. And the relative gains and costs are important to consider, because successes and failures might provide learning gains in different ways, right? Someone's incorrect, but was confident that might be quite surprising to them, and there's evidence that that can direct their attention better and result in what's called hypercorrection. So they learn very, very well from being incorrect, and surprisingly so. But successes can be very fast while providing learning gains. And so the relative gains and time costs of these different aspects of a learning event are really important to consider. And I see I have some questions here. But that's basically, that's all the slides, I think.
Yeah, and so, you know, to kind of drive that home, I think I sent a couple of questions to Neil, and one of them was, you know, a lot of these models may have, especially the transformer ones, may have better fits than logistic regression, but how do we use them to make predictions in the system? And also too is maybe maybe an AI approach can really do better than, you know, sort of the analytical approach of, you know, analyzing the curves that we use, and kind of, you know, enhance on some of these intuitions and really go deeper on how AI can affect pedagogy and not just prediction.
So I think it's great you guys are bringing up actually you're bringing up actually an answer to a question I was planning on asking in the discussion, but I'll just state it here so all of my presenters can think about it. But two things I'm really kind of curious about, because Luke was just kind of like saying, well, here, maybe a good question is, when we do more competitions, what types of competitions would be most beneficial for the field? Luke was just actually already asserting, wouldn't it be cool if we could actually figure out how to actually model the world where the task is, you know, optimize the whole loop, which is actually, you have to pay attention to the fact that if you actually give them feedback, you know, if they get it wrong, you have to give them feedback. That takes some amount of time. Our goal is to learn, not just predict stuff. Anyways, I guess I want you all to be thinking about actually what are the types of competitions that actually we should think about in the future. But with that said, since I know we could go a little while on that, and I know that I've purposely been letting things slide a little bit, and my organizers are starting to freak out. And actually, Neil, are you losing track of time too much? Hey, can we all thank our speakers for the moment? Okay,